Okay, hello 115 students. Here's some mini lecture time for chapter 7. I'm going to talk to you about energy and chemical bonds, heat changes during chemical reactions, and something about why chemical reactions occur having to do with free energy is coming, but that means I describe entropy to get there. The exothermic, endothermic reactions will be covered in class soon. Alright, so these are the goals that we're covering. What energy changes are that take place during reactions. We need to think about factors that influence energy changes in chemical reactions. And in learning about what free energy is, we're going to have to be able to explain a little bit about enthalpy, but more specifically today I'm going to talk to you about entropy. And we'll work towards free energy changes a little bit later. So, simple definitions about energy, types of energy. There's two broad types of energy. One's called potential energy and one is called kinetic. Potential energy is that energy that is stored. It's waiting to be released. Things like water in a reservoir behind a dam, an automobile poised to roll downhill, the pencil at the edge of the table ready to fall off, a coiled spring, and chemical bonds also have potential energy. Kinetic energy is energy of motion, and energy of motion, anything that is in motion, has kinetic energy. And so water falling over the dam after it's been released from its potential energy status, this turning a turbine, which has motion, and a car rolling downhill, all those things have kinetic energy. So springs uncoiling also have potential energy, and molecules in motion have kinetic energy. So we'll talk more about kinetic energy as we move along in this chapter. Those are just terms to know. Part of what accounts for heat changes in chemical reactions is the notion that there is energy associated with chemical bonds. It takes energy to break a bond, and that's called bond dissociation energy. So if you've got shared electrons, breaking them apart, separating two atoms, breaking bonds requires energy, and the converse is also true. Making bonds tends to release energy. So some simple examples are shown here on this slide. If you take two separate nitrogen atoms and combine them to make the N2 molecule, it releases energy. Releasing energy, it goes along with the stability of sharing electrons between two atoms. In this case, it happens to be a value of 226 kilocalories per mole of nitrogen molecules formed. If you combine two chlorine atoms to make a chlorine molecule, you end up with a slightly different value, a significantly different value, much less, fewer kilocalories per mole of chlorine molecule formed. And in fact, this is directly correlated to the idea that you have a triple bond in nitrogen and a single bond in chlorine. So the more bond formed, the more energy involved. So the reverse will also be true. Breaking apart nitrogen takes more energy than taking apart chlorine molecules. So here we have it on the next slide. So if you take a nitrogen molecule and add sufficient energy to separate it into two atoms, it requires that same value, 226 kilocalories per mole. Or if you're breaking apart a chlorine molecule, it takes 58 kilocalories per mole. So this is called a bond dissociation energy. The amount of energy required to break a bond in those molecules is described in kilocalories per mole. You will notice that the amount of heat required to break a bond is very much the same numerical value as the amount of heat released in forming a bond. So the amount of energy in the two senses is the same. One of them is required and one of them is released. So this brings out the idea of what endo and exothermic are about, which was discussed somewhat in class. Endothermic and exothermic are very important terms to hang on to. Endothermic reactions have energy required, energy input is required, and so breaking a bond requires energy. And these two examples at the top of the slide show examples of reactions that are endothermic. The reverse is true. If you are releasing energy, that's described as energy being given off. Energy is exothermic reaction here. So energy, when heat is given off or heat is released, we describe those processes as exothermic. So a second thing to notice here is that the reverse of an exothermic process is always endothermic. So breaking a bond is the reverse of making a bond. So one will be exothermic, one will be endothermic. And that's very numerically exactly the same as you can see from these examples. Third concept to notice here is that the amount of heat transfer that accompanies a change in one direction is numerically the same as that for the change in the opposite direction. In other words, you have energy required for one and energy released for the other, but the numerical value is the same. One of them is it's going to be 226 kilocalories required to break apart nitrogen molecules into atoms, and you release the 226 kilocalories per mole when you form a nitrogen molecule. So these are related to some laws that we don't talk about in detail, but they kind of make sense, hopefully. The law of conservation of energy tells us that energy can neither be created nor destroyed in a physical or chemical change. We can tend to keep track of where some of this energy goes as we think about heats of reaction. The heat of reaction is given a fancy name called an enthalpy change, or the symbol delta H. You can think of H as meaning heat, which totally is acceptable, makes sense, or it fits. So the amount of heat released or absorbed during a chemical reaction is described as its enthalpy change, or delta H. And so it's specific to a physical or chemical change what that delta H value will be. It has to do with where it comes from. Delta H is related to the energy required to break bonds, and you subtract from that the amount of energy released in bond formation, and you come up with a value for delta H. We're going to talk about delta H values quite a bit more in the rest of this chapter. So you'll use delta H values to understand about whether reactions are going to proceed or not. You're going to require energy for reactions that are endothermic, and you're going to release energy for reactions that are exothermic, and how that pertains to delta H will be described later in class. The other thing that we need to describe, though, is what makes things tend to be spontaneous. Spontaneous reactions are those that tend to happen without further encouragement once they've begun. Water will always flow downhill, down a waterfall, given an impetus to get it going. They will lead to a lower energy state by going down the waterfall. Well, this same kind of idea applies also to reactions, and it's described in terms of what makes reactions spontaneous. Spontaneous reactions are those which occur without further external influence once they've begun. So pushing the pencil off the edge of the desk means that the pencil is going to keep on going once you push it. The reverse of a spontaneous process will therefore be not spontaneous. So if it's going to be spontaneous downhill, it's not spontaneous going uphill. And those kinds of things require continuous external influence, some kind of energy added to keep them going. We will commonly think of spontaneous processes as being those that are exothermic because they give off energy, but it's not always true. Ice melting, you think of being spontaneous, but it's only spontaneous as long as you're at a warm enough temperature. At a cooler temperature, ice does not melt, and you'd have to add energy to it to make it melt. Perfume dissipating in the room is the same thing. Perfume will commonly dissipate quite readily, but that's if you're at ordinary temperatures. If it's cold enough, they will require the addition of heat to allow perfume or something fragrant to dissipate. So that tells you that there's more than just whether or not, so back up. Both of these processes are therefore endothermic. They require heat to be added to them to proceed. And so those processes can be spontaneous, but it depends on the temperature. So things that determine the spontaneity of a chemical or physical change has to do with two factors: whether or not the heat is absorbed or released, in other words, exo and endothermic reactions. If it's released, it's exo. If it's absorbed, it's going to be endothermic. And we'll talk about how that affects delta H, but not right away today. And then the second factor is the increase or decrease of entropy. That helps to determine whether a reaction is spontaneous. Well, what in the world is entropy? I think you all have gotten a good idea about it from simply reading its definition because you answered it successfully on the quiz. But entropy is a funny term. It is a measure of randomness. It's given the symbol S, which seems illogical for that term, but that's what's used. It means randomness or disorder, and entropy in the universe is naturally always increasing. The tendency is always towards disorder. If you look at your dorm room, your backpack, or what the activity of a 2-year-old is about, that's what disorder is, and it naturally occurs unless you fight against it. So cleaning your house is battling entropy. So whenever entropy is in a positive value, a change of entropy is positive, that means that it's a favorable process because the entropy is increasing. It's whenever entropy is increasing, that's a favorable thing. So becoming more random is favorable. Examples of that would be when a solid is producing a gas, or as shown at the bottom of the screen here in this diagram, when a solid turns to a liquid, that's an increase of entropy, or a liquid turning into a gas, or a solid going all the way to gas. Any of those are increasing entropy. The more motion and disorder in the molecules, the greater the entropy, or the increasing entropy. Or another version of understanding entropy is to think in terms of how many moles are present in a system. And so if you have 2 moles of reactants and it turns into 4 moles as product, well, something is breaking apart apparently, and have 4 moles in your products means that there's more randomness. So when you ever go from fewer moles to more moles, that's also an increase in entropy. Entropy decreases are therefore the opposite of each of those statements. So let's take those and see if we can apply them to some examples. If you have a deck of cards nicely stacked up, you shuffle it up and you make a mess all over the page or all over like it's shown on the right, entropy is increasing. That's a positive change in entropy, delta S. So delta S is greater than 0 when entropy is increasing. Total disorder. So when you have the opposite sign, delta S being negative, that means the process is unfavorable. The entropy is decreasing and things become more orderly. And so things like freezing of water into a solid, in other words, liquid turning into a solid, is a decrease, get the words carefully here, a decrease of entropy. So liquid going to solid is a decrease of entropy, not a favorable thing. It takes effort to freeze things into an orderly pattern. And so you have to remove some heat from the molecules, among other things. So more examples. If you took a beaker full of little spheres, little wooden beads, and apologies to anyone who don't see the colors here, but the top part is, whoops, back up. The top part is all green beads, green spheres, and the bottom part is all red. If you're colorblind, this may not be obvious to you. If you stir it up, entropy has been what? Well, it's more disordered on the right, and so this is an increase in entropy. When you have mixed them all up, delta S is greater than 0. Change in entropy is an increase of entropy. Much more disorder when you have stirred them up. These examples are sort of easy to think about once you get used to them, but we have some more fun ones that are actual chemistry examples as well. So let's look at a couple more. Try to determine whether the change in entropy is an increase or a decrease in these examples. So if you have iodine, iodine occurs normally in a pure form as a solid. If it sublimes to make a gas, is this an increase or a decrease? Well, think about it for a minute. If you are going from a solid, it's going to be in a crystalline form in an orderly pattern. And if it's in a gas, they're all moving all over the place. So they're very random. Increasing randomness, that's increasing entropy. What about sodium reacting with chlorine to make sodium chloride? And we've seen that reaction in the video, if you were noticing. And so if you take sodium atoms that are solid and chlorine gas and combine them to make a solid, that's an interesting one because you have here a solid and a gas. making a solid. And so there's more order in a solid than there is in a gas ever. So this one happens to be a decrease in entropy. So the symbol for that is minus delta S, or it's a negative value for delta S. Delta S is less than 0. You don't have to factor in heat in this particular discussion to decide anything about entropy here. But if you're going from a gas, solid in a gas, to just a solid, in the general sense, you're going the other direction. You've decreased your entropy. Now, last one on the bottom of the screen, last example for today, is to look at the nitrogen and hydrogen reaction making ammonia. I've told you that one is a very common example. It's used for lots of things. Well, how do you know if entropy is increasing or decreasing? And it's all gases here. There's nitrogen gas and hydrogen gas making ammonia as a gas. Well, here's where you have to count the number of moles. Well, this is easy counting because you just look at coefficients. No math to do there, just count. Well, a little math. And on the left side, we have 4 moles. And on the right side, you have 2 moles. So if you're going from 4 moles to 2 moles, you're going to make fewer moles. That is a decrease in entropy. Change in entropy, again, here is less than 0. All right, these are examples that will get you started on entropy, and we'll talk more about free energy later as we've had a chance to discuss the values of delta H being positive and negative and how that all factors together.